You share the link on Slack?
I didn't, but should do that. Yeah, exactly. I think you're good to go.
Okay, thanks. Hello everyone, thanks for being here. And so my talk will be about functional programming 101, or the basics of functional programming. So like everyone knows, functional programming is gaining a lot of popularity lately. Everyone is trying to learn it. Everyone thinks it's the new cool kid. So, but functional programming is not that easy to learn. It comes with a lot of hard concepts, a lot of new concepts that are very different from typical imperative concepts. So what I'm trying to do here is to focus on the basic and simple concepts of functional programming. Okay, so we know that functional programming comes with a lot of jargon, a lot of complex words, a lot of words that we don't know what they mean. And there is a GitHub, a link to a GitHub page here, which it has all the functional programming jargon that just take a look at it and it's scary as hell. So I'm not going to talk about all these concepts. I'm just going to focus on the simple one. But the matter of the fact is, you need to learn all of these complex concepts. You need to know them, but you don't have to know them to get started. So you can start with easy concepts. You can do functional programming with other languages other than Haskell. But if you want to be an expert or like an intermediate functional programmer, you have to learn these concepts. So for people who wanted to learn what monads are today, I'm sorry in advance. We're not going to talk about that. Okay. So one thing that we all know about functional programming is that everyone says it doesn't have an exact definition. Like everyone, if you look at talks on YouTube or conferences, everyone will start his talk with a different definition. But the thing is, it makes sense because there is a lot of areas that functional programming touches on. And it depends on the speaker or the teacher, which area he wants to focus on. So we have all these definitions. And actually, functional programming encapsulates all of them and much more. So for example, people say it's programming based on function calls as the primary programming construct. And that is opposed to imperative programming. So in imperative programming, we know that we have commands. So your program is a sequence of commands, one after another. But in functional programming, is actually nested function calls. So a function calls another function, and a function calls another functions. So the return value of the first functions is actually the input of the other function, and so on. Other people say it's actually, they focus on purity. So functional programming is all about pure functions. So how to avoid side effects, how to isolate them, and how to manage them properly. So we're going to talk about purity later. Others say that functional programming is actually programming without state. And that's actually a very good point, because as imperative programmers, we are used to declaring variables, assigning them, working with them. So we are used to working with state and reassigning the state and changing the state. And it's a big hurdle when you're trying to do the transition from imperative programming to functional programming. So you're looking at the problem, and in your mind, the first thing you're going to think about is to declare a variable or a counter, and then to track its state, but then you can do it in functional programming. So it's a very tricky thing. Another expression is actually programming with expressions instead of statements. And that's not actually only for functional programming. It's declarative programming. So in declarative programming, we only program with expressions. We don't have statements. We don't have loops. We don't have control flow. We don't have if. We don't have branching. And functional programming is, in functional programming, everything is an expression. We don't have control flow, and we'll talk about this later. The last thing that you're going to hear a lot about functional programming, and it's the thing that scares a lot of people, is actually it's based on lambda calculus, which is a mathematical model of computation, as opposed to Turing machine. So we all know Turing machines. They're like, they describe computation as manipulating symbols through assignment and evaluation that depends on time. But lambda calculus is about, it describes computation as application of functions that are independent. The order of evaluation is independent. And to be actually clear about this, lambda calculus is the backbone of functional programming. But most functional programming languages, they don't implement purely lambda calculus. So they are inspired from lambda calculus. And there's another computation model called recursive function, which is another computation model. So most languages will try to take ideas from both computational models. Okay. So we're gonna just try to focus on some basic concepts to just give you a taste about functional programming and what are you gonna face if you try to venture into the world of functional programming. So I think that the first thing we have to accept or get used to is that everything is an expression. Expressions are the building blocks. So like I said, we don't have loops, we don't have control flow. So even if the branching, we don't have it. It's also an expression. Okay, so first thing is, what is an expression? An expression is everything that can be reduced to a value. So we have primitive values, our expression 1, 2, 3, characters ABC, functions are values, and so functions are expressions, and you can create compound expression by combining functions with values and other expressions. So you have very complex expressions that are built from other expressions. I forgot to mention variables, which are some symbols bound to values, and we're gonna see what's that important. So everything is an expression, and actually your whole program, if it's built in a functional way, is actually a very big, complex expression that is built from smaller expressions. And if you can please bring the slide. Sure. So here you have the type signature of if. So like I said, if is an expression. So it's this is its type signature. So if you don't have if into your functional language, you can actually create it. So it's actually just a function that takes 3 parameters. So the first parameter is a Boolean. So that's the predicate we're gonna test. And the second and the third arguments are the values that we are going to return. In case if it's true, we're gonna return the first one. If it's false, we're gonna record the second one. And you have to, you're gonna notice that the last A is actually the type of the return value. And when you see A, that's actually Haskell. So the return value of the if function, the type of the return value of the if function is actually must have the same type of the second and the third argument. So we know, so if you have an expression, okay, I'm just gonna talk about referential transparency and then you're gonna see the advantages of expressions. Okay, second thing is, so when everything is an expression, we have a constraint and a big benefit, which is referential transparency. So what referential transparency means is that since everything is an expression, and we know that expressions, they reduce to a value, so we can go to a compound, complex expression and replace some expressions with the value they reduce to. So I can replace it by its value or by its another function, or I can replace it by the function that's reduced to the same value. And it's an easy concept, but actually it has a very important implication. So let's say you have a compound expression, and we have some sub-expression that is very complicated. So we can actually just replace that complex expression with its value and focus on it and look at it and try to reason about it. But the implication here is that if we're going to replace an expression, which might be a function, this function must be pure. So if it's not pure, if it does something on the side, if it has a side effect, we cannot really reason about our code, because if we're going to replace it with its return value, it did something on the side and we didn't know about it. So the constraint of referential transparency means that our expressions and our function must be pure. We must make sure that they don't do any side effects, they're not mutating anything. And the other benefit of referential transparency is something called substitution model. So if we have the referential transparency in our program, like I said, we can replace expressions and sub-expression with their values. So actually, it's like you're solving a mathematical equation where you have x and you have y, and it doesn't matter what you call it, and it doesn't matter what you replace x with, because it doesn't matter. X might be equal, I don't know, some other complex mathematical equation, so you can just replace x with its value. And actually, it makes it easy to reason about your code, and it actually show how functional code is really modular, because you have all these expressions that you can replace, that you have referential interface, you can just take one, replace it with its return value, and then think about it. Take the other one, test it, think about it, reason about it, try to understand it. So this is the big benefit of substitution model that we have thanks to referential transparency. I hope that was clear. If it's not, okay. So we talked about expressions as building blocks. So everything is an expression in functional programming. Now we're going to talk about purity. So we were talking about pure functions. So pure functions are functions that return the same output given the same input, always. And we can actually divide the definition of pure functions into two main conditions. So deterministic. So the function is deterministic. It means that given the same input, it always gave the same output. Like no matter where you run it, no matter what is going on the outside world, the function will always give the same output. And it's actually a mirroring between functions in mathematics. So a function in mathematics is defined by function f, if given the value g, will always return n, no matter what. So that's deterministic of function. The other condition of pure functions is that they don't have side effects. So they don't log to the console, they don't make network requests, they don't communicate or interact with the outside world. So this is the two conditions for pure functions. Now, pure functions, they have like I can think of three benefits. First one is memoization. So if our function is always going to return the same value when given the same input, we can just cache it. So if I give f1 is going to return 20, I can just cache it. So because I know whenever I'm going to call f1, it's going to give me 20. So I can cache it and like reset ease. Second one is laziness. And not a lot of functional programming languages are lazy, but some of them are. Haskell is one lazy function. Laziness means that the language will not, okay, I'm just going to give an example. So suppose we have a function that returns a list from 1 to 100. And I'm going to call a function. I'm going to apply this function to this function that returns the list from 1 to 100. And let's say my function will be take 5 from the return value of this function. So take 5 will just take the first 5 elements from the list. But my function will return the whole list from 1 to 100. So actually, the language will not evaluate from 1 to 100. It's just going to evaluate the first one, second one, until 5, and then it's going to stop the evaluation. It's not going to evaluate the whole. And we have a lot of gain in performance here. But actually, it adds some complexity, and so it depends. It depends on use cases. because sometimes it's unpredictable. So that's why a lot of other functional programmers don't implement laziness. And we have parallelization, which is pretty easy to do with functional programming, because like we say, our functions are pure. So we know that they're going to always return the same value. So if we want to do parallelization, we can just split our input and give it to different functions and run each one of them on a different thread, and then we can merge the results. So we don't have any shared state, and we know that our function will deterministic, so they're gonna return the same value. So we can just do it without worrying. So that's about pure functions, which is a very crucial concept in functional programming. The third thing I want to talk about is state immutability, or statelessness and immutability. So first thing we have to know is that pure functional languages, they don't have statements. Like, you cannot assign to a value. You can declare a variable, which means you're just gonna have this, you're gonna say, I have this symbol, I want it to have the value 5. That's it. If you're gonna, it's usually done with the equal sign. So if you're gonna call the same symbol with the equal sign another value, the compiler will yell at you, it's already bound to another value, so you cannot do it. So you don't have assignment. You cannot change the value of the variables you declare. And so that's what I talked about early on. It's, as imperative programmers, we are used to, first thing we do is declare variables, and then we're going to track them, and then we're going to reassign, and then we're going to change them. But in functional programming, that's the big thing you're not going to be able to do. The bad news is many functional programming languages, they allow assignment. Few of them don't allow it. So you can always fall to your old habits. So we'll talk about later about which functional programming you should start with, but just know that a pure functional language will not allow you to do assignment. So you should not think in terms of assignment. Second point is data structure are immutable. So in functional languages, you cannot change the state of your data, never. Always, when you operate on a data structure, you always return a copy with the changes. You never modify the original data structure. And that's a common concept nowadays, because most languages, they have either immutable data structures. For example, Python has tuples, and tuples which are immutable. The other data structures, if they're not immutable, you can just bring in a plugin or a package that has collections that are immutable, like lists or maps or something else. I said earlier that the third point is aim for statelessness. And I said earlier that there are many talks on YouTube, but when you check them out on YouTube, they're gonna define functional programming as aiming for statelessness, like don't use state at all. And if you if you have to use it, try as much as possible to isolate it. So the aim is always not to use states. We're gonna see there are other ways to, program without state, program without variables and assignments, but that's the aim. Like, always don't declare variables, don't try to reassign them. And if you have to, many languages have other mechanism or concepts to do how to deal with state. And there is an example of a Fibonacci function in Python, and you can see this is very imperative. So we declare variables, and then we assign E and a B, and we have a loop, which we don't have in functional programming. So this is something you can never do in a functional language. Okay, so state, immutability, and we talked about that we don't have control from functional programming, but we must have loops, because loops are programming. So the way we do iterative processes in functional programming is through recursion. So everyone knows what recursion is. It's a function that calls itself until there is a condition, and it's going to stop. So we have a recursion Fibonacci in Python and Haskell. In Haskell, it uses pattern matching, but don't care about it too much. So recursive is actually a very, very important concept in functional programming. And the most crucial thing that you have to learn when you start functional programming is that you need to have a solid understanding of recursion, because it's used everywhere. Many built-in functions in the function language use recursion, and even data structures are built in a recursive way. So it's a very crucial concept. Function languages are also criticized for heavy use of recursion. So as you can see in the Fibonacci, it's not a tail recursive call. So this is very bad implementation. One thing that we can do to improve this code is we can memorize the function. So when we are calculating Fibonacci of 5, when we cache it, the program is not going to calculate again. It's just going to get the value of it. And some function languages, they have the tail call optimization built into the language. So if, for example, I think Scala, if you give it this Fibonacci, it's going to transform it into a recursive call function. Some languages don't have the optimization, so you have to write tail recursive functions yourself, which is part of why people criticize functional programming for being too hard. Okay. So it's called functional programming, so it's all about functions. And functions are the primary construct. So first thing that a functional programming language has is functions as first-class citizen. And what that means is that functions are values. So you can pass them as parameter, you can return them from other functions, and you can store them in some data structures. And the thing is, many languages nowadays have this property. So they have some Python, Ruby, many languages, they're not functional languages, but they have this property. So you can actually, you have some aspect of functional programming. Anonymous functions are called lambdas, so they're functions without name. And so you usually use them with higher order functions. So you have your higher order functions that takes a function as a parameter, and the function you're gonna pass, you're not gonna use it anywhere. So why give it a name if you're not gonna call it anywhere? So you're just gonna see them a lot pass an argument to other functions. And also, most programming languages now, even imperative or object-oriented, they have this property. Okay, higher order functions, and this is the thing that you're gonna see a lot in functional programming, are functions which either they take a function as a parameter, or they return a function as a return value, or both. So these are called higher order functions. And for example, the map functions, it takes a collection and then it takes function and applies that function to the collection. We have function composition, and it's the same as in mathematics. So you have, I think it's called f round g. So you have f round g applied to x. It means that you're going to apply g to x, and then the return value of g applied to x is going to be the input of f. So you're going to see function composition a lot in functional programming. And you have the dot sign, the point, which is called the composition operator. So you can compose f and g, and you can just store the result on another function. So I can have function h equals f.g, so I have a function, so I don't have to worry how it is implemented. I just know that it's going to take x and it's going to return some value. Querying, which is a very important concept in functional programming as well. And it means that, so your function, instead of taking many arguments, you turn your function into a function that has many functions, and each one takes an argument. I screwed that up pretty bad. So I'm just going to show you an example of querying, so you can see it in action, and then you can understand the concept. Well, one thing about functional programming is that when you learn it, it's always very difficult to explain to people. That's the curse of functional programming. It's the curse of monads, it's the curse of functional programming. It's very hard to explain. But so I have a JavaScript here, JavaScript library called Lodash, and it has a query function. So that's this function. It's gonna transform my function into a function that's gonna take the argument as Okay, I'm just gonna explain it. Okay, I'm just gonna remove everything here. Called silence, was it, or close? Okay, so I'm just gonna have the function add, and it's gonna take E and B, and it's gonna return E plus B. That's my function. It's an add function. It's a pure function, and I'm just gonna apply the query function here to transform my function into a queried function. Okay, so I pass it add, and I can console log. Add. Again, if I give it 2, 3, let's see what it does. Yeah, I should give it the queried because that's the one I care about. So queried is the queried version of the add function, and if I run it, it's return 5, so it keeps the same behavior. What we're gonna do now, and this is exactly querying, is that I'm gonna pass the first argument. I will only pass this first argument, which is 2. So query 2, I'm just gonna pass the first argument, and then the result of this application, I'm gonna give it 3. So that's querying. So the application queried applied to 2 will actually return to me a function that is expecting the second argument. So that's querying. And defined. It returns 5. And just one thing to see it in action, I will console period. I'm just gonna pass it the first argument. Function wrapper, and if I do this type of it's a function. So you can see that what query did is actually, instead of having the function take multiple parameters, it's gonna expect one parameter at a time, and in each application, it's gonna return a function that expects the second parameter. So query of 2 is another function that is expecting another argument, so it can return the value. So that's queried. That's querying. And in lambda calculus, all functions have one argument, and Haskell and ML, which are function languages based on lambda calculus, they are by default, they are queried by default. So all functions, they are, if you have multiple arguments, it just means that behind the scenes, it's just gonna transform them. Right. Another thing, it's called partial application. So the second thing that I did, it's called partial application. So when I have my function that is queried, and I choose, for example, I have division that expects the first argument, second argument, I can just call division of 1, and this one will return a function to me, and I can just call it another name, and it will expect another argument so it can do the calculation. So that's called partial application. So instead, I can just fix one argument, and so apply that function in one argument and fix it, and assign it to another function, and I can just work with that function. That's called a partially applied function. Wow. This way. Okay. So yeah, we have Korean partial applications, and these are concepts that you're gonna see a lot in function programming. Like I said, Haskell and ML function are queried by default. So when you have your functions take 3 parameters and you apply 1, it's always gonna return a function to you. It's not gonna return error or anything. And so la renaissance of functional programming, which is it was actually the motive for me to give this talk. And I was asking a lot of questions because functional programming was around since the 50s with Lisp. And there was Erlang, there's a lot of languages, but we only hear about it, we started hearing about it lately. So what's the reason? Why? There is an interesting Hacker News thread that you should read. People discuss why the sudden hype about functional programming. And with my research, well, the first reason is that it's cool. It's very cool. We are very hipster. We are very different. We're just going to use functional programming. We are cool. We are smart. And another reason is that in Silicon Valley, you hear about these startups that are worth $1 billion. And actually, in their stack, they are using Erlang or Elixir or Scala. So of course, when you hear that WhatsApp has 10 employees or 15, and they are worth $1 billion, so you're gonna be curious about their stack. So why are maybe they are worth $1 billion because they're using functional programming language, which is stupid, but people tend to pay attention to that. Another reason that you're gonna see, you probably saw a lot in the internet, is that a lot of people are complaining about, oh, OOP is bad, OOP is dead, OOP didn't deliver its promise, without that OOP is the answer to all our complexity. And I think it's bullshit, because it's us, the developer, who failed in OOP. So people, they need some kind of justification or an excuse to move to something else and hope it's gonna solve their problem. So these are like maybe personal reasons, but another valid reason is that computers are faster now and the memory is cheap. So in the 50s, computers were very slow and memory was very expensive. And functional programming, as we said, that it uses heavily recursion, and you can easily write non-recursive functions. You're going to use a lot of memory, and people weren't ready to trade performance and speed for this kind of expressiveness of functional programming, for this safety of functional programming. But now we have very fast processors, we have a lot of memory, so it makes sense that we go back and give functional programming another shot. Parallelization is another reason, and people now, we have very fast processors, but we have multi-core, so we have to make use of these cores. If you have 8 or 32 cores, so you need to use them at base. So parallelization it's easier to do with functional programming, because most of your functions are pure, and you have total control about side effects. So it's easy to do, and if you have a problem, it's easy to reproduce. Another reason is actually JavaScript. So there is one language for the web, and it's called JavaScript. And JavaScript has a lot of aspects of functional programming. And it's actually based on Scheme, which is another dialect of Lisp. And since JavaScript is very popular now, everyone is talking about it, and it's made some people actually explore this origin and root of JavaScript. So people actually trying to explore the origin of JavaScript in terms of functional programming. And one thing that's actually made functional programming the mainstream thing in the front-end world is the React framework. So React framework is a framework that is declarative. It's a framework that sells itself as a declarative, functional way of building and coding JavaScript. So because JavaScript has a lot of beginners and a huge community, a lot of people, so people are not afraid anymore about diving into functional programming. So, because in the beginning, everyone, if you talk about functional programming, everyone says it's something that is academic, something that is very hard, something that is very complex. But now, everyone is just, even though they're not learning about monads and about complex concepts, they're learning about the basic concept that we talked about. So, pure functions, side effects, recursion. So, it's made it lowered a little bit the entry level to functional programming. Okay, so this is the last thing I want to talk about, and it's if you are interested in learning functional programming, well, actually you have to ask yourself, is it worth learning, because like I said, we only talked about a small set of features of functional programming, but there are more complex sets. And with these concepts that we talked about, you can actually do them in multi-paradigm languages. So you have Python that you can do functional programming with, JavaScript. So you don't have to go into very strict FP languages. But that wouldn't actually be very beneficial, and that's my personal opinion, because functional programming is a different paradigm. And paradigms are about the things. There is a paradigm shift. So you have actually, when you're learning functional programming, you're gonna learn programming from scratch. And if you wanna do that, it would be best if you admit that you don't know how to program, and you give away, and you actually start learning from scratch. Because there is a huge, we talked about you can't mutate state, you can't code with state. So a strict functional programming language will be beneficial to you more, because it's not gonna let you do the things that you used to do. So it's not gonna let you assign, it's not gonna let you mutate. It's gonna be hard to write bad code in a strict functional language. So there is this book called Structure and Partition of Computer Programs. It says it's the best book about functional programming, and it is. But it's a big book, and the exercises are not that easy. So if you're patient, if you have time, and you're actually ready to learn about functional programming, just give this book a try. If you, like, my advice would be to choose a strict functional programming language. So you have Haskell and you have Elm. Haskell and Elm both are pure functional languages, but Elm is actually more of for the web. So if you're a web developer, it would make sense for you to check out Elm. Clojure and Elixir are new kids also on the block, and they're very popular now, but they're dynamic languages, so you don't, it would be better to have types, but yeah, everyone has an opinion. So my personal choice would be for you to learn Haskell. If not, it's up to you. Okay, before I finish, there is one thing that I wanna mention here. There is this, I don't know if you can see it. Yeah, you can't. Okay, so yeah, so this is a ladder of functional programming. It's a very recent post or picture made by the organizer of the Lambda conference. And they came up with something very smart. So in conferences, you have workshops. And like I said, in functional programming, there is a lot of concepts. Some of them are easy to grasp, some of them are not easy to grasp. So they made this ladder that if you're gonna do a workshop and you're gonna cover, for example, immutable data and second order functions, which is just first level of high order functions, or construction, destruction, function composition, you like add to your workshop so that it's for novices or beginners. If you're gonna talk about algebraic data types, pattern matching, okay, so actually your workshop is for advanced beginner. And there are more and more actually concepts. So for expert, there are other concepts. But I see this document as a very good guide for you if you're interested in functional programming. So if you grasp the first set of concepts, you know that you're above beginner. And if you move to another set of concepts and you grasp them, you know that you're an intermediate and so on. So that's a cool thing. And yeah, I think that's it for me. That was my talk. Yeah, if there's any question, I'll take questions.
If there's anything on the slide. Nope. So no questions?
No questions? So is that good? Cool. Well, I guess thank you for being here. Thank you for listening to me.